We are in module 2 discussing transformation and complex integration. In today's class we are discussing complex integration, under which we have three subtopics: line integral of a complex function, derivation of Cauchy's theorem and Cauchy's integral formula, and in what way this Cauchy's theorem and Cauchy's integral formula makes things simple for us in evaluating the complex integrals. Now, out of which in today's class we will discuss line integral of a complex function and derivation of Cauchy's theorem, and verification of this Cauchy's theorem is discussed. In next class we will discuss Cauchy's integral formula along with its problems. Okay, to discuss line integral of a complex function, it works quite similar to the integration whatever people have seen under vector integration. But still, if you don't remember that concept, it's fine. I will try to give my best to make the things simple for you people. So please try to understand. Okay, let me consider my first example to understand this. Evaluate integration of z square over the curve C, where C is the square having the vertices 0, 0, 1, 0, 1, 1 and 0, 1. Now let me draw this curve. So this is what the curve is. So curve is a square. Square is a closed curve. It's a closed curve with this four vertices 0, 0, 1, 0, 1, 1, 0, 1. And it is not a compulsion like you have to go with anti-clockwise direction. You can also go with clockwise direction, but it is left to us. But whatever we are taking, it should be decided in the beginning itself and we should act according to that. So right now I'm just dealing with this in anti-clockwise direction. So with this is my C1, this curve is C2, this is C3 and this is C4. Now keep this in mind. So direction makes a difference. You people know that. So now if I want an integration from A to O, so that is a negative of integration from O to A. You people know that whenever we interchange the limits of the integration, sign of the value changes. So that is what we should remember. Now let me come back to this example again. So now integration over C is nothing but integration over C1 plus integration over C2 plus integration over C3 plus integration over C4. So now if I take z is equal to x plus iy, and we get dz is equal to dx plus idy, and z square is nothing but what? X plus iy whole square, that is a plus b whole square formula should be used to have x square plus iy whole square, that becomes minus y square plus I 2xy. So now let me consider the curve C1, along which let me try to evaluate this integral. So now along this line, so this is C1 is a line connecting the points 0, 0 and 1, 0. And observe this line carefully, along which you can find, so the value of y is constant, that is the value of y is 0. So which means this curve C1 represents y equal to 0 for us. Y is 0 says the value of dy is 0. If dy is 0, what happens to this dz? That just becomes dx. Which means that in this integrand the value of dz is just dx, because we have the variation only with respect to x in this case. Now by using this, your integration reduces to this form. Integration over c1 z square is given by, so since y is equal to 0, so this is 0, this one is 0, z square is nothing but what? It is just x square dx. I are integrating with respect to x, and see along this curve what is the variation of x, and you can note that x varies from 0 to 1. So that is what I have taken here. Integrate this with respect to x and substitute the upper limit, and the lower limit is 0, that makes the value 0 for us. So value of this integral is 1 by 3 along the curve C1. Now consider C2. Along C2 you can find the value of x is fixed, that is x is equal to 1 here. Which means dx value is 0, there is no change in x, so dx is 0. If dx is 0, what happens to dz? That is I dy. So if you consider this integral again, that is equal to, in this expression put x is equal to 1, that gives 1 minus y square plus I to y. That is what I have written here. dz is written. Everything is expressed in terms of y. I need to know the variation of y along the curve C2. Along the curve C2, y varies from 0 to 1. That is what I have taken here. Integrate this and substitute the upper limit minus lower limit. You will end up with this expression. Now let me consider C3 now. So C3 is a line drawn from B to D. So which means along this line you can note the value of y is constant, that is 1. So I should take y is equal to 1 in it, and dy becomes 0. So my dz once again dx. And if I substitute everything back in this expression, so x square, y is 1, so it is plus I to x. You are integrating with respect to x and see the variation of x here, that is from 1 to 0. Integrate that and substitute the limits. Your answer is 2 by 3 minus I. Now do the same thing with C4 now. Along C4 you will find the value of x is constant, that is x is equal to 0, dx becomes 0, so dz is once again I dy, and substitute all these things back in the integral. So z square is just minus y square now because the value of x is 0, and with I dy you have everything expressed in terms of y. So I want the y variation where y varies from 1 to 0, and that gives I by 3 as my answer. So now we have found the value of the integration over all these curves. By adding them we get our answer. So integration over c z square dz is given by integration over c1, that is 1 by 3, integration over c2, integration over c3, and integration over c4. If you just add them, you will end up with the value 0. Okay, I hope you people are comfortable with this. Let us see our next example. Now evaluate z square plus 2 over the curve C. This curve C is given by this figure. Now have a look at this one. C is what? Is a line joining the points 0, 0 and 2, 1. So along this line, it is not like the previous problem. Here both x and y are varying. So what should be done then? And we know the equation of line joining the points x1, y1 and x2, y2, that is given by y minus y1 divided by x minus x1 is equal to y2 minus y1 divided by x2 minus x1. I have my x1, y1 0. This is 0, this one is 0, this one is 0, and this one is 0. And x2 is 2, y2 is 1. So 2 and here it is 1. So it is y by x equal to 1 by 2, or y equal to, or x is equal to 2y, or y is equal to x by 2. So now this line represents y is equal to x by 2. Now it is our choice now. It is not like the previous problem. In the previous problem we found that along one curve, along a line, we had only one variable was varying. But in this case both y and x are varying. Now it is our choice now. Now if I expressed everything in terms of y in this case, so I should take the variation of y. Or if I express everything in terms of x, in that case I should take the variation of x. Now just to avoid the fraction and all, I will just go with substituting the value of x, and I will express everything in terms of y in this problem. Now z square plus 2 is what? X square minus y square plus I 2xy plus 2. And in which if I substitute x is equal to y, we will get this. This is 4y square minus y square, that is 3y square, plus I 2, x is nothing but 2y, so it becomes 2 2s are 4, 4y square plus 2. And we know if I consider the value of dz, so dz is what? Dx. Okay, so x is nothing but what? 2y, that is what I have written, plus I dy. So differentiation of 2y is nothing but what? 2 times differentiation of y. So that gives 2 plus I dy. Substitute everything back in the integral. So that is 3y square plus 4y square plus 2, 2 plus I dy. Where I am expressed everything in terms of y. Take the variation of y, where y varies from 0 to 1. Substitute in it and evaluate this integral. Your answer is 1 by 3 times 14 plus 79. And if you want to check out this one, instead of substituting for x, you substitute for y, and in that case everything will be expressed in terms of x, and you should take the variation from what, 0 to 2. That is what the variation of x in this case. Now if I consider the second curve, so this is also a curve between the same 2 points 0, 0 and 2, 1, but on a different path. Here it was just a one line connecting these 2 points. Here we are moving along C1 first, so then we are moving along C2 to reach B. So which means we are talking about the same 2 points. Between them we are interested in finding the integration, but along a different path. Now if I consider this one, it is quite similar to the problem of a square, so I'm not explaining much here. Along this line we found the value of x is varying from 0 to 2, the value of y is 0, and if I put y equal to 0 in this, you will get x square plus 2, and x varies from 0 to 2, and you know that when y is 0, your dz just becomes dx. Integrate this, you have your answer. And along this line the value of x is fixed. Put x equal to 2 in this, and with that, so this is what your expression, and since x is 2, dx becomes 0, we just get I dy. Integrate this with respect to y and substitute the limits. This is what your answer is. Now integration over this curve joining the points 0, 0 and 2, 1 is given by sum of these two integrals. So that is equal to 1 by 3 times 14 plus 17i. Now let me consider the third problem. So here I am considering a triangle with the vertices 0, 0, 2, 0, 2, 1. I am just taking the anti-clockwise direction again. So along the curve C1, so you can note that the curve C1 is same as the curve C1 which I have considered here. C2 is nothing but the same curve C2, and C3 is nothing but this curve but with a negative orientation. Here we have found the integration from 0 to 2, 1. Here we are supposed to find the integration from 2, 1 to 0, 0. Now if I consider this integration C1 is known to us, I will write that answer. Integration C2 is also known, we can write that one. But over C3, so this is what my answer is, from 0 to 2 or 0, 0 to 2, 1. And you know, if I take the negative or if I just take the integration from A to O, it will be what? Negative of this value. Let me substitute that here, and by adding them your answer is just 0 again. Let me consider the next example. So next example goes with the same 3 paths or curves, but I am going with a different integrand, z bar whole square, and z bar is nothing but x minus iy whole square, that is x square minus y square minus I to xy. Now I don't want to talk much about the orientations and all, I'll just get into the problem directly. So along this line, so okay, 2y equal to x, I'm just taking x is equal to 2y in this one. So this is what my expression is. So that is 3 minus 4i y square. Further, your dz value is what? D times x is 2y plus I dy, that is equal to 2 plus I dy. Substitute these two things in this expression. And since everything is expressed in terms of y varies from 0 to 1, integrated, substitute the limits. So this is what you will get. But if you come to this one, the same thing happens, but with z bar whole square. So put x is equal to, put y equal to 0 along this line, and you will be expressing everything in terms of x, that is just x square, our integration is 8 by 3. And afterwards along this curve, so x value is 2, put x equal to 2 in this, and we have the y variation that is from 0 to 1, integrate this, so that gives the value of this integral. Now just add them to have your value along this curve joining the same 2 points 0, 0 and 2, 1, and you have got 1 by 3 times 14 plus 11, 9. Now come back to this one. You people already know what should be done. So C1 value is known to us, C2 value is known to us, and for this one I should take the negative of this, that is what I have written, minus 5 by 3 times 2 minus I. By adding them you have, this is your answer, 4 by 3 times 3 plus 4i. I hope you people are comfortable with the line integral now. Let me consider one more example in this case. I'm supposed to integrate from 0 to 1 plus I along the path y is equal to x, and next time along the path y is equal to x square. Now let me try to understand one by one. So let me just draw the graph corresponds to this one. So y is equal to x is what? A straight line passing through the origin. So 0, 0 and 1, 1 both lies on this line. So now I'm supposed to integrate from 0, 0 to 1, 1 along this curve C. Okay, and this represents y is equal to x. So just like the previous problem, what should be done now? Since y is equal to x, dy becomes dx. So then what is your dz? Dz is dx plus I dx, that is 1 plus I times dx. So if you can just get into the integration, put y is equal to x in it. So that gives x plus ix plus 1, and dz is this. Integrate this one, x square by 2 plus ix square by 2 plus integration of 1 is x between the limits 0 and 1. Substitute the limits and you will end up with this answer, just 1 plus 2i. Now consider the second path. So this is a parabola. Y is equal to x square represents a parabola. I'm supposed to find a integration from 0 to 1 plus I which lies on the parabola y is equal to x square. Now do the same thing again. Since y is equal to x square, what is dy? This is 2x dx. Then what is your dz? Dx plus I times dy is 2x dx. So it is 1 plus I 2x dx. Good. So by using these values and substituting everything back on this, it gives x plus ix square plus 1 and this 1 plus I 2x dx. Just multiply them. Both are polynomials. Just multiply them. And this is what your expression. Integrate this with respect to x, and you have from this point to this point. Since I have expressed everything in terms of x, so I should take the x variation that varies from 0 to 1. And on substitution, okay, note you will once again end up with the answer 1 plus 2i. Next example, it's x square minus iy dz along the same path y is equal to x and y equal to x square. I have considered different integrand but with the same paths and same points. So if I put y is equal to x in it, so and on integration, so I will end up with this answer 5 minus I by 6. In this case, if I substitute y is equal to x square, and it will be our expression here 1 minus I is should be taken out, which is a constant, and x square was common here. X square is multiplied to this one to have this expression. Integrate, substitute the limits, and on simplification your answer is 5 plus I by 6. Okay, so next let me consider a circle case. Z minus a whole power n dz. I'm mentioning it that n is not equal to minus 1 in this case, where the curve C is the circle mod z minus a equal to r. So mod z minus a equal to r represents what? A circle with center at a and the radius r units. So for this one, mod z minus a r is equal to mod z minus a equal to r is equivalent to z minus a equal to r e power I theta, because e power I theta becomes what? Cos theta plus psi sin theta, and modulus of e power I theta gives square root of cos square theta plus sin square theta, that is 1. So modulus of e power I theta is 1. So if I take the modulus of this, modulus of z minus a is equal to modulus of r e power I theta. R is just a real constant. Modulus of e power I theta becomes 1. You will get back to this. Now z minus a is fine. I can substitute on this one. And what about dz? For a given circle, radius is always fixed, only theta varies. So dz is r is constant. Differentiation of e power I theta is I e power I theta d theta. So and theta varies from 0 to 2 pi for a circle. So now consider the integral and substitute the limits for theta, z minus a value and dz value, and r is constant, it is kept outside. So integrated here and substituting the limits. Here e power I theta is there. E power I theta is nothing but what? Cos theta plus psi sin theta. But keep this in mind, cos, this is an even number. Cos even integer pi, that is cos 2 pi, cos 4 pi, cos 8 pi, all this becomes 1. And whereas sin integer pi is always 0. So as a result, you will get e power I times n plus 1 2 pi value is just 1. By substituting that here, it will be 1 minus 1, the value of the integral is once again 0. Now have a look at this next example, dz by z minus a, where c is the circle, mod z minus a equal to r. So I just given the explanation for mod z minus a and all. How do we get this one in the previous example? Here, if I substitute everything back in this expression, you will get IR e power I theta. So that is your dz, and z minus a is written. R e power I theta cancels. I is constant. Integration of 1 becomes theta between the limits 0 and 2 pi. The answer 2 pi I. Okay, so I hope you people are comfortable with line integral of a complex function now. Next, let me see Cauchy's theorem and its importance. Here's what the Cauchy's theorem states. If f of z is analytic and f dash of z is continuous at each point within and on a closed curve C, then integration of f of z over the closed curve C is 0. So this is what they are saying. We have a region D enclosed by the closed curve C. Now if f of z is analytic in this region and also on this boundary, so then it's a closed curve. Keep this in mind. This is a closed curve enclosing this region D. So if that is the case, value of this integration becomes 0. What is very important here? You are supposed to claim f of z is differentiable function. That's very important. Okay. Analytic means differentiable. People know that. Okay, if I just put f of z is equal to u plus iv and x is I plus y, z is x plus iy, means dz becomes dx plus I dy. Substitute these two things back in this expression. Okay, and I'm just multiplying them. So that is done here. Okay, u dx plus iv dx, u I dy, I square is minus v dy. Afterwards, separate the real and imaginary parts. Real part is u dx minus v dy, and imaginary part is I is taken common, v dx plus u dy. Let me call this as equation number 1. So now it's a time to use this given f dash of z is continuous. This means that if f dash of z is continuous, the first order partial derivatives of u and v are continuous in the region D enclosed by C. In this region, you can prove these are continuous functions. So if that is the case, we can make use of the Green's theorem, and this is what the Green's theorem states. If m and n are real valued functions having continuous first order partial derivatives in the region D enclosed by C, then integration over m dx plus n dy is equal to this. Here you can note that here u and v in both the integrals are satisfying these conditions. As a result, I can employ this result for this one. So in equation number 1, integration over C f of z dz is equal to, here the role of m is played by u and the role of n is played by minus v. You just substitute in this, you will get dou of minus v by dou x minus dou u by dou y dx dy. Next time the role of m is played by v and the role of n is played by u. As a result, you will get dou u by dou x minus dou v by dou y dx dy. Here what we are doing, the line integral is converted into what? A surface integral. That is what is done. So now observe this carefully, and they have given one more condition, f of z is analytic. What is the meaning of f of z is analytic? U and v satisfies CR equations. And observe it carefully, dou u by dou x is equal to dou v by dou y. As a result, the difference between these two, this difference becomes what? 0. And you will find dou u by dou y is minus dou v by dou x. So it will be minus dou v by dou x plus dou v by dou x cancels again. So this will end up with integration of f of z over the closed curve C is given by 0. But you should keep this in mind. Converse of this result is not true, which means you are finding the integration of f of z over some closed curve C and you got the value of the integral is 0. It doesn't mean that the function f of z is analytic, but it is always, whenever the function is analytic, you can note that this integration becomes 0. And before verifying this one, let me see one simple corollary on this one. And this is what this corollary says. Let me explain this corollary through this graph, so this figure. Here they are saying that P and Q are the 2 points. I am interested in integrating f of z between the points P and Q. If that is the case, this corollary is saying that you can consider any 2 paths, or you can consider any path along which you can move from P to Q. You can consider any path along which you can move from P to Q to find the value of this integral, because irrespective of the path you are considering, the value of the integral remains the same. That is what this result says. But the thing is, the curve which you are choosing, that should lie within the region. Okay, you have f of z which is analytic inside and also on this closed curve C. You have proved that one, and afterwards you are saying that you are integrating f of z from P to Q. If that is the case, you can choose any curve along which you can move from P to Q to have the value of this integral. That is what it is saying. So now to do that, this is what if you just observe it carefully, I am chosen the point A on PQ, and on the curve theta I am choosing the point B. So now if I just observe it, if you just observe this one, it's a P, A, Q, B, P. This gives a closed curve for us. This closed curve C in D. And we are saying that the function is analytic in this entire region. If that is the case, the function is analytic in this region and also on this closed curve. If that is the case, by Cauchy's theorem, the value of this integral should be what? 0. But C represents what? C can be written as integration from PAQ plus integration from QBP. And we know that integration from QBP is the negative of integration from PBQ. So as a result, this integration reduces to this form. And PBQ represents C2 and PAQ represents C1. And taking this to the right hand side, we have integration of f of z over the curve C1 is same as integration of f of z over the curve C2. Now let me try to analyze Cauchy's theorem and its corollary through the examples which we have already discussed under line integral. Let me start with my first example, which we have discussed already, and we have already proved this. Integration over c z square dz is 0 here. Here I need to talk about this. Why we are getting the value of this integral 0? So is it possible for us to connect this to the Cauchy's theorem? Yes, it is possible. Have a look at this integrand. Integrand f of z is what? Z square in this case. Z square is a differentiable function. It's a differentiable function in the entire complex plane. If that is the case, we can claim the f of z square is analytic in this region and also on this closed boundary. As a result, you can note the value of the integral is 0. So from now onwards, you keep this in mind. So before start evaluating the integral in the regular method, first just check whether the function is analytic or not. If the function is analytic and if you have chosen a closed region to integrate, so then you need not to go for the integration. You can directly claim the value of that integral is 0. Let me consider the next example. Have a look at this third case. We consider the closed curve and the value of the integral is becoming 0 here. Look at the integrand z square plus 2. It is once again what? A polynomial, and that is differentiable at every point in the complex plane. As a result, integration, since it is analytic in this region and also on this boundary, value of the integral has to be 0. And along with that, you can note your corollary 1 is satisfied here. Here we are integrating from 0, 0 to 2, 1. Here also we are integrating from 0, 0 to 2, 1. But the difference is here we took a line along which this curve is moving from 0, 0 to 2, 1. But here we have considered C1, so then along C2 to reach that point. But you can note that value of these two integrals are exactly the same because of this corollary 1. Since the function f z square plus 2 is analytic in this entire region, whether you are considering this curve or this curve doesn't make any difference. You will end up with the same answer. That is what this says. If I consider this next example, z bar whole square dz. Now have a look at this. Value of the integral is not 0 in this case. And also you can note that between the same 2 points, we have got 5 by 3 times 2 minus I, and that one is different from the value what we have got for the same 2 points here. So which means what is wrong with this integrand? Let me just check out that. So z bar whole square is this, which means u is real part is x square minus y square, imaginary part is minus 2xy. Find dou u by dou x, dou v by dou x, dou u by dou y, dou v by dou y. You can note dou u by dou x should be same as dou v by dou y. These two are not same here, and dou v by dou x should be negative of dou u by dou y, but these two are becoming equal. So which means both the conditions are not satisfied here. As a result, we can claim z bar whole square is not analytic. We know that whenever the function is analytic, u and v has to satisfy CR equation, but that is not happening here, which means f of z is not analytic. So that is why the value of the integral is not 0 here. So in such kind of problems, that is whenever the integrand is not analytic, no option for us. We are supposed to make use of a regular evaluation of line integral method to find the value of the integrals. And you can note, consider the same 2 points, but still we are ending with the 2 different values of the integration. Okay, if I consider this example, here you can note 1 plus 2i, 1 plus 2i, integration between the same 2 points but along 2 different paths, but you have got the same answer. The reason is x plus iy plus 1 is nothing but z plus 1. It's a once again what? Analytic function. Because it's a polynomial, it's an analytic function in the entire complex plane. So not only these two curves, you can just also consider circle which passes through 0, 0 and 1, 1, even along which it won't be an issue, we will get the same answer. Okay, now it is left to you people how you handle that. Let me consider the next problem, x square minus iy. So but in this case you can note we have got 2 different functions, which means is there any problem with this? Let me just check. U is x square, v is minus y, dou u by dou x, dou v by dou x, dou u by dou y, dou v by dou y. You can note dou u by dou x is not same as dou v by dou y, failed, which means this function is not analytic. So obviously we are not expecting same value for these two. We are not expecting same value for these two integrals. These two has to be different, or they can be same. They can be same because of some other reason, but it is not because of the Cauchy's theorem or its consequence. Next example. In this case, you can note that so f of z equal to z minus a power n, it becomes an analytic function. It's an analytic function in this region and also as well as on the boundary. As a result, you got this value of this integral is once again 0. There is no flaw, that is there you can differentiate this function at every point in this region. But if I consider this next example, here f of z is given by 1 by z minus a. That is in the previous example I am supposed to take n is equal to minus 1. So this is what the situation is. Here what happened, when you take z is equal to a, you are getting the denominator is infinity. So please keep this in mind. When the function goes to infinity, at that point we have a flaw. So at that point the function becomes singular. So since the function is becoming singular here, or the function is not analytic at the point z is equal to a, and that point here lies in this region. We are not saying the function is analytic at every point in this region, because at the point z is equal to a, it is not analytic. As a result, we are expecting something else for this value of the integral, but if you get 0, it may be because of some other reason, not because of Cauchy's theorem for sure. So this time it is 2 pi I. Thank you all. I hope you people are comfortable with this. If you have got any doubts, so please come back. Thank you all.